Thank you very much. Thank you for the introduction and for the invitation to be. It's a real honor to be a part of this wonderful conference in memory of Jan Nekovář. I never had the good fortune to meet him, but I have admired his mathematics ever since my first introduction to his writings, which was the expository writing I remember well on the Bailin's conjecture. I want to start with one way, his preferred way, I suppose, to write the functional equation in the general setting, and then specialize to the setting of GSP4 and in my title. If we have a pure motive in the sense of the article, which is a compatible system of elliptic representations in the cohomology of smooth projective variety, say over the number field Q, and then we have the completed L function by suitable gamma factors, and it is expected that this completed L function is entire holomorphic, entire meromorphic on C, with maybe just finitely many poles at certain rational integers, and the functional equation, which in the article of I mentioned, is written in this way for the completed function, where there is an epsilon factor, which is of the form an exponential in a linear function in S, e to the a plus bs, and then we have the dual motive twisted by 1. So I immediately switched to this more concrete setting, but in this framework, the question is, what can we make a sense of taking square roots of this L function, and then that inherits the functional equation. However, we deal with functions that are not entire holomorphic on all of C, but a multi-valued holomorphic function. And my observation that so the point that I would try to exploit is that on the one hand we have this Dirichlet series with integrality property of its coefficients. So it's a Dirichlet series with maybe rational integer coefficients. I write in the p to the minus s over the primes p. And on the other hand, this square root function has a single valued holomorphic branch on the complement of any compact, of any closed set in the complex plane that pairs up the zeros of the L functions. And so in the connection to arithmetic algebraization methods sets up this question to, in what sense, so if k is sufficiently small, this will be analytic, on a very analytic somehow, and we want to play this out against the integrality of the coefficients. So here is a concrete theorem in this setting, with just one more bit of just technical notation. So for a ring R, let's denote. I want to consider divisors of L functions. So and maybe I'll introduce some ad hoc notation to be the R module of discretely supported. So these are formal R linear combinations of points in C. I can think of them discretely supported mappings to C. So they are the divisors of holomorphic functions. And a theorem, I'll write a couple of them. And this in itself is joint I should say. What is a ring. Any ring?
Supported from C to R, that or from R?
You're right, sorry. Thank you for, yes, I mean R linear combinations of with coefficients in R of points in C.
Also, when you say pairs after zeros, you assume that the algebraic number of zeros is...
Yes. We assume that taking account of multiplicities.
It is even. Is it always even? No. It's
no. Okay.
there are many zeros that
maybe you let him state the theorem.
Yes, the theorem should make it clear. Okay, so the theorem is a concrete case of this setting. So this in itself is joined with Frank Calegari, but it uses, so it's work in progress. And this will be the qualitative theorem that I hope to earn the right to ask a question by showing some, at least some new result. I would like to refine this to a quantitative Diophantine approximation style theorem. But I should say before stating it that the bulk of the work is in our joint paper by the three of us, Frank Calegari, myself. So that builds on the previous work, and Yunqing Tang, on the unbounded denominators conjecture, which is available in the archive from 2021. And so I will propose a new way to think of this result, and that allows to prove something in this framework. Okay, so it states the following. Consider the map from isogeny classes of elliptic curves over Q, modulo isogeny. And then I take the completed L function and take its divisor. So that defines an element of this Z of C divisor. And that map is injective by the Falting's isogeny theorem and combined, I suppose, with Adamar's theory of factorizations of entire functions of finite order. So this L function is a finite order 1. And then I can take the reduction map modulo L. So let's say let L be a prime. Okay, and the result states that this composite map is still injective. And theorem B, so this is like for a case of GO2 cross GO2. And let me state the second theorem right away and then discuss this pairing up business.
At divisor, you mean just look at the zeros and close?
Yes. So I just say if the L function has, for example, only zeros of even multiplicities. So if I, for example, take the product of the L functions of two elliptic curves, and if they have the same reduction modulo P, then for the product, the L function, the zeros are exactly doubled up, and so the square root is holomorphic and inherits a functional equation on C. So the idea is that this square root would then look like a GO2, the L function of a GO2 modular form, and the task is to prove that modularity, that it's actually it actually is GO2 modular form. and based on the integrality properties of the Dirichlet series and the formal expansion of the square root. Okay, so theorem B also. Let A over Q be an abelian surface. Then the following are equivalent. So for abelian surfaces, it has only been proved that the L function is meromorphic at this point, so this comes from potential modularity, and the last step of the proof, which is the same like in Artin's conjecture, the Artin-Brouwer theorem. So by the theorem of Boxer, Calegari, G, and Piloni, this L function is known to be meromorphic. And so now I say part one, the L function is actually holomorphic. There's a huge difference in this field, entire holomorphic function. And on of C, and then, of course, by the meromorphic result, it does inherit the good functional equation and good growth properties, and has zeros of even multiplicities. So this is part one. And this, of course, should happen if and only if A is isogenous to the square of an elliptic curve. So we need some sort of a converse theorem to read off, or to some criterion for a function of this form to be attached to a modular form. So point 2 means isogenous to the square of some elliptic curve. And the theorem says the following are equivalent. In this subject, so let's observe that in much more generality over in the function field setting, or let me keep it just down to earth, in the case of abelian varieties over finite fields, all such results are immediate corollaries of Helmholtz theory. If you have abelian varieties, then you have its characteristic polynomial of Frobenius, and if it's a perfect square of another polynomial, then that means the variety A is isogenous to the square of another abelian variety. But unfortunately, so in this arithmetic case, we can prove very little compared to the conjectural picture. Is this grand simplicity of zeros, which should prescribe that if we have any abelian variety, then firstly, so of any dimension, the L function should be entire, and it should have, so it has a functional symmetry with S goes to 2 minus S, and all the zeros, let's say if A has no multiple isogeny factors. This is like having a separable polynomial in the analogy. And then in this case, in fact, all the zeros should be simple apart from the center of the critical strip as S equals 1, which governs conjecturally the Mordell-Weil group. It can be a multiple zero of high order, but so this type of conjecture completely subsumes these results. But this is something that we can actually prove. let me state now what I mean by almost doubling the zeros in the sense of this compact K. So here's my prototypical observation or little result over finite fields. I found this result, so this is an unpublished theorem from a couple of years, I think 2021, which was which is essentially the same argument that I used to solve a conjecture of Shinzon-Zassenhaus, and this so this theorem I call the CM analog for Shinzon-Zassenhaus bounds. It is a separation result for zeros of Weil polynomials. It says the following. So consider abelian varieties over finite fields, FQ. And I will, it will be a completely explicit inequality, but maybe I prefer to think of a fixed finite field, but the regime that the genus dimension of A goes to infinity. And then we so we have this Weil system of Frobenius eigenvalues on the circle of radius square root Q. And let's say to keep it simple, I assume the dimension of A is even, say 2n. And then I have 4n Frobenius eigenvalues, which are symmetrical the reflection on this circle, and I'll draw them. Okay, so half of them lie in the upper half of the circle. Maybe these points where the real points plus minus square root of Q could be one of the zeros, but they come with even multiplicities. So, and if I have a multiple zero, maybe here, I just draw. So I want to say on this picture that there is a canonical interlacing of the zeros. I just starting from say this point, I go in the counterclockwise direction, and so just interlace the zeros. Alpha 1, beta 1 is the first segment that I take, and then you have alpha 2, beta 2, a union of segments, and maybe if some of them coincide, so this segment alpha 4, beta 4 degenerates to a point of length 0, and then the inequality is a separation bound for the total arc length on this circle. Let me define this, sorry, as a delta of A invariant of A to be. So how closely this is to the square of an abelian variety, taking the sum of total arc length of this interlacing. Alpha I, beta I, 2n points. So this is some number between 0 and the total arc length, which is 2 pi square root of Q. So Honda Tate, of course, tells us that if that delta is 0, if and only if A is isogenoous to the square of an abelian variety. And then if delta of A is not 0, how small can it be? The theorem is this explicit inequality. The first term, which is simply exponential in the minus the dimension, but the main term is Q to the power this exponent minus n minus 1 over 2. And so this is not a particularly striking result in itself, that it's no surprise we're dealing with separation bounds for algebraic numbers. And of course, there is a general Mahler-Mignot bound coming from the fact that you have resultants or discriminants of integer polynomials that are not 0, rational integers are at least 1 if they're not 0. But this, so I want to point out that this bound of Mahler and Mignot, based on discriminants, does not gives a inferior, worse exponent roughly by a square. and that this bound that I will take as my blueprint for the proofs of these theorems A and B, and for what I would want to ask for L functions later on. So this method gives the optimal result essentially. So this is the best exponent of Q. And the proof is connected, so I just say one-line sketch of, it's connected to the Andrei lemma, or this method of arithmetic algebraization from Yunqing's talk in Transcendence. So it's applied to the following formal function, which is another square root of, let me take a formal, so power series expansion, expanding the Newton binomial. Sorry, I want to pair up those 2n roots on the circle. I take the traces of them to the interval, and so what I do is the following. The trace of alpha I over x. Okay, so far each of these linear polynomials in 1 over x, I mean the square root of that has its Newton binomial expansion with almost integer coefficients, with actually algebraic integer coefficients, because I put this factor of 4. But then also, so that's not the whole story, of course, I assume that alpha I and beta I are very close, so I put this companion factor. And then, so observe that this is using complex multiplication. Okay, this is actually has rational coefficients, and it also has integer coefficients from what I just said. So it defines a formal integer power series in 1 over x. I view that as a formal function on the Riemann sphere, on the projective line centered at infinity. So the complex multiplication being from, if we want to get to the optimal bound, from this complex conjugation commutes with the other complex embeddings. So these traces I've written down are actually also a complete set of.
What you about Ji and
beta, alpha I and beta I took their traces to the interval minus 2 square root q, 2 square root q. They are totally real algebraic integers, totally contained in this interval. Okay, so I have this function, which is on the one hand, it has integer coefficients, and is also holomorphic. It has a single-valued holomorphic branch on the Riemann sphere minus the union minus the following k, where k is the union of those 2n segments. I put in a factor of 4, alpha I plus alpha I bar, and 4 beta I plus beta I bar. Those traces. Okay, so the rationality criterion of Poya applied to this situation, which indeed can be fits very naturally into a common framework with the Andrei theorem that Yunqing presented. Now, it states that a formal function with integer coefficients has to be a rational function as soon as it has analytic continuation to the complement of a compact with transfinite diameter strictly smaller than 1. And so I can read that off contrapositively, since obviously I wrote down a quadratic algebraic function, but not rational function. This is inequality, which is already a separation bound on this compact K. So the separation bound reads transfinite diameter of K is at least 1. And one can transform this ultimately in terms of the total arc length. It entails this separation bound. So that first, so this by transformation formula of Robinson, or Raphael Robinson, translates into the capacitance of the original set of circular arcs is at least q to the quarter over 2. And then but there's a bound in the other direction due to Haliste, which is very geometric and intuitive, that if you have a given number of arcs on a circle, in this case those 2n arcs, and in terms of the total arc length L, the configuration that maximizes this transfinite diameter is of course a rotationally symmetric case where you have exactly n bounds. Okay, so that's distributed into, okay, say the given number of arcs times each having the same length L over n. In that case, you compute the transfinite diameter explicitly, and there goes that is exactly the separation inequality. So now I'm trying to do something similar in the L function setting. And let me try to also highlight why I'm, okay, I first want to prove the qualitative theorem, but why I'm so interested in trying to extend it into almost double zeros extensions. This comes from, I think, the main motivation is to recall how the class number 1 problem was solved, okay, or the history of this iconic part of number theory, that there was firstly Deuring's analysis where he analyzed the Epstein zeta function of a quadratic form. Let's say we have a primitive reduced quadratic form ABC of discriminant, a negative discriminant minus d. Then this Epstein zeta function is, of course, just a special evaluation of Eisenstein series at this Heegner point minus b, the root of the quadratic polynomial. Yes, this point, which reduction means that it, a Gauss reduce means that it lands inside the standard fourth fundamental domain of SO2Z. The Fourier series expansion of the Eisenstein series, sometimes connected to the also Chaulas-Elberg, looks like there is a highly convergent error term, so to say, which Deuring considered an error term. And this comes from, so it looks, let me just copy my formula. If I have y is the height of this Heegner point, so this is square root of d on 2a. And of course, the point is that if we had a quadratic imaginary field of class number 1, this point is as high as it can be, giving the principal quadratic form. Actually, it should be more like on the boundary, identified an ambiguous class. And okay, with this notation, T of S, and one more, maybe I prefer to complete this zeta function, just for sake of, it's more convenient this way. And T of S is this very simple main term but U of S decays exponentially in minus y because of it's related to, it comes from the non-constant Fourier modes in the Eisenstein series, and it's related to Bessel function. I'll try to nevertheless very quickly write that down without much comment. So it's some series divisor function, and then you have this culprit for this exponential convergence, the Bessel function 2 pi n y. Well, finally, k of z is given by this integral 0 to infinity e to the minus z t plus t inverse over 2 t to the s minus the half d log t. And so if we have, so this is Deuring's analysis in 1933, if we have, just by Rouché's theorem, a 0 up to height y of this completed quadratic form L function has to be, well, okay, so firstly, this term t of s plus t of 1 minus s overwhelms what is equal to the absolute value of u of s, which is very small, which is exponentially small in e to the minus y, sorry, in minus y. And so, by a bit of complex analysis, he showed that the zeros has to be simple, okay, either simple and lying on, sorry, has to be simple and either lying on the critical line or just close to 0 or 1. And these latter zeros do indeed exist. There's just a unique such 0 for y sufficiently big. And so the logical paradox was that, so of course this couldn't be the completed, for arithmetic reasons, the full zeta function of the quadratic field, unless the Riemann, so he, in this way, he concludes that either the Riemann hypothesis fails or that there are only finitely many class number 1 quadratic fields. And soon after that, by Heilbronn, the same analysis works for twists by any Dirichlet character. So we can replace the Dirichlet zeta function by any non-principal Dirichlet character c and twisting in this way by chi minus d. And however, since so this was the first historical proof that there were finitely many class number 1 fields, because anyway the Riemann hypothesis for Dirichlet functions directly implies that. So now observe in this analysis that if we have, so firstly that then in 1949, everyone, I believe, everyone agrees now that the first complete solution of this class number 1 problem was the one found by Hegner, but essentially a solution was given by Gelfond and Linnik and completed by Baker and Stark later. In 1949, which was starting from this analysis and taking auxiliary Dirichlet character psi, which they unfortunately restricted to be of prime conductor. They should have taken a composite conductor, like, and that would. But so basically, they consider the limit of this evaluating with the Kronecker limit formula of exactly this L function. And that leads to, so for example, if we take psi to be the real, say, even character non-principal of conductor 21, then these formulas give rise to a small linear combination of logarithms. One of them is the fundamental unit of this number field Q root 21. Logarithm of an algebraic integer with coefficient is some integer that is from the class number formula, happens to be the class number of minus 21d. And then pi. And by this exactly, the this exponential decay of the error term in the approximation Deuring considered, we get a linear form in 2 logarithms, which would be exponentially decaying, exponentially small in e to the minus square root d, if I keep c fixed, but linear and with coefficients being algebraic integers from this field q root t. Or we can even get them to be rational integers, and with multiplicative height bounded by polynomially in d. That contradicts the Baker's theorem, or Gelfond-Baker theorem, on linear forms in logarithms. Such a lower bound, if it's not 0, has to be always polynomially bounded below in this height h. The coefficients of the linear forms, once we fix the arguments of the linear forms. And so there are just finitely many d's to check, because everything here is effective in principle. But unfortunately, with more Heegner points, if they don't lie, all of them lie up in the fundamental domain, this analysis, this approximation, does not allow to reduce to linear forms in logarithms. So I want to observe that in this, so now the observation is immediate. The solution of this problem looked at s equals 1. And we can step down a bit to the complex plane. So the upshot of this scenario would be that, say, I take 2 characters, C1 and C2, of, let's say, non-principal, and of some conductor, the same conductor, chi, k, common, and fixed. And so these functions, L s psi1, L s psi1 times our supposed exceptional character, and similarly this one, would have their zeros both zeros all up to height square root of d localized to certain, to exponential accuracy in minus square root of d, to the same certain points. So the solutions of this equation, t of s plus t of 1 minus s. However, there's this twist in C equal to 0 inside the critical strip. So that means that I can pair up, so for the product, and I really want to take, so the square root, so that means a holomorphy on a large region of the product of those for Dirichlet functions. Okay, the zeros of this and the zeros of that can be paired up by exponentially short line segments of lengths exponential in minus square root d. And this, of course, is a very similar, very basic situation, and it's not a new problem. But there is a lot of so new situations where this analysis can be applied. And for example, just to say, if we don't assume class number 1, let's say bounded class number, all we would need is that these characters C1 and C2 are not the same character, but the multisets over the reduced quadratic forms A, B, and C of C1 of A and C2 of A are equal. And then we have chi sufficiently bad Siegel 0. Then there is a similar, that I will not quantify for want of time, similar matching by short segments. So it's not, so I want to give the qualitative proof of the theorem, theorems A and B, and ask if what should be the analog of this theorem for the Weyl numbers. So the results on simple zeros this ground simplicity hypothesis has very little progress in this setting, but I think for GL2L functions, the main progress comes, of course, so there are infinitely many simple zeros, proof for any GL2L function, which is not just the square of a declared L function, and coming from Conley-Gosch for the normal jump delta function. And then this inspired the work of Andrew Bucher and then the converse theorem of Bucher and Krishnamurthy. And somehow originally, so this was a refinement of the Weil converse theorem for GL2 in the original simplest setting GL2. And similarly, it turns out that so our tool that I'll state now is another completely different refinement of the Weil converse theorem. And then, so this was in 2003, but years later, I made, I believe, relatively recently, Bucher found twists to back to use the original idea that inspired him on the original problem of simple zeros. What Conley and Gosch had done in their paper is that if they had it basically would work for any elliptic modular form as soon as they found one simple zero. And Bucher found basically found that his proof of the converse theorem applied to that. And so by now, for example, for elliptic curves, I believe to me the state of art I know of is that has this L function has at least a certain power of simple zeros up to height t. But there is nothing apparently that has been made to work for the product of two such L functions or for GSP form. So for higher rank groups than so this is just for the elliptic modular forms. And so just one last word about how Bucher connected these two converse theorem analytic ideas. So basically, the converse theorem refinement of Weil that he did was that so Weil had to assume that we have a holomorphy with good analytic properties and functional equations for all the character twists, or for sufficiently many of the GL1 character twists of a given L function to conclude that the L function is indeed comes from an elliptic modular form. This refinement could relax holomorphy to meromorphy for all but one of the twists, and he still had to have holomorphy for the remaining twist. And so the idea back to simple zeros was to consider for an L function the following Dirichlet series, which is taking the derivative of the logarithmic derivative, multiplying by L, and observe that for this for this L function, the poles are exactly the simple zeros of L. Now I'll state, okay, so the connection to, so he obtains a contradiction from the existence of just one pole of one twist of this series, and this came from Euler factors. So the main observation, the main idea in this paper is that if we take any L function and twist it by the principal character modulo some q, then this L function has you just pull out Euler factor of f, and that Euler factor for elliptic modular forms that are not just say in this case for cuspidal elliptic modular forms are just simple. Usually have no multiple zeros, so that gives the one simple pole of some twist of this d of s. Now I state our, finally, refinement of the original unbounded denominators conjecture, and which we view as a converse theorem with for Dirichlet series with rational integer coefficients that look like they should come from an elliptic modular form. So the theorem is the following. So let me give that a name, integral converse theorem. Integral meaning that I want to consider only one L function and not any twists, but also that I assume integrality of the coefficients. Work in progress. I dated to this here. So consider a power series f of q with s integer coefficients to allow some leeway. So I have a finite set of primes that I'm allowed to invert. But I also assume that in the framework of Yunqing's lecture, this tau invariant is equal to 0. But let me just be more down to earth. I say, so I assume that it has s integer coefficients for some finite set of primes. And I assume that it converges on the periodic unit disk for all primes, including for the ones so convergent on this unit disk. So the denominators are not too bad, including for p in s, or p dividing s. Okay, so that is the thing I'm trying to prove will be a modular form of some weight and level. So now we need some data. We have a companion, so we need to consider functional equations. So suppose there exists some integer n, or integers n and k, positive integers, and some companion Dirichlet series. Let me call it. Dirichlet series means that as soon as I have f, I take its formal Milan transform L of s. I'm just putting the Dirichlet, the power series coefficients as Dirichlet coefficients. And so suppose this has a companion that I will denote L tilde of s, for which I don't assume any integrality properties, just some complex numbers, a n tilde, a n to the minus s. Okay, complex. And they should be connected. So firstly, they should be meaningful Dirichlet series that, as Dirichlet series, both converge absolutely on some right half plane. Okay, real part is bigger than some sigma naught. And they should have, then I need to complete in the GO2 style. So I write lambda of s and lambda tilde respectively to be, so I want to think of n as ultimately being the conductor. So this is the way to go for the functional equation. So the power s, this factor e of s, epsilon, and then there's the gamma factor, and then there is L of s. And similarly, I'll just write exactly the same for lambda tilde, of course only replacing L by L tilde.
L tilde was again?
I say, suppose they exist on L tilde. So the data is like ends on the first line. It's just this power series. So
A n tilde is the same as what's the relation?
A priori, I assume they just exist. I mean, there's just some complex numbers.
But they have a relation with a n or not?
Oh, yes, in the end they will. But yeah, so suppose they just exist. And suppose these functions are entire have, well, already they're defined in some half plane, entire continuation, entire holomorphic, it's crucial not meromorphic, to O of C. And say of order of growth 1, or if you prefer, bounded in vertical strips is in general unrelated, but also works. So it's an alternative choice of well-behaved growth. Okay, so and finally, with the functional equation that we expect. So suppose these exist and they're related by lambda Ves equals I to the k lambda tilde of k minus s. Then the conclusion is what you expect, that f is a cuspidal elliptic modular form of weight k for the group gamma 0 of n. And how we apply that, I would say the two theorems at the beginning are almost an immediate application of this. Well, immediate granting, of course, the modularity theorem and respectively the Caligari, this Boxer, Caligari G, Piloni theorem for the abelian surfaces. But my point is that this condition, so in the framework of Junching-Stauch, the integrality properties imply tau equal to 0. And this is sufficiently lax to guarantee to be automatic in the settings. So just as in the model theorem, I had the binomial expansion of the square root gave me an integrality property once I just had this factor 4 put in by hand, so to say. Here I don't even need the factor. So just observe that if you have any normalized Dirichlet series, just a formal Dirichlet series, I'll put the first zero, so n equals 1 coefficient is 1, and then you have some integers, let's say plus a2 to the minus s, and so forth. This is how, I mean, all L functions coming from a motif will have these integer coefficients. Sorry?
Could you lower the middle?
Oh, yes. The middle, sorry. Just one second. Yeah.
So original condition of convergence, it's for one p or it's for every p?
Every.
Yes.
Okay.
For every p, including the ones in S. Okay, so
Tau invariant condition is weaker than this one? Or you originally had this tau invariant?
it just tau equals 0 is all that matters. It's yes, so it's implied by this.
Okay.
Yes, and so you have a Newton binomial which gives you some denominators of 2, but they are very mild. So you just take this remainder term, and then you use the Dirichlet series rules, just multiply them, and k1 to 0 to infinity. And so you get something, so you take s equal to 2, it has some denominators. I guess I put like Dirichlet series in this notation of p prime. But the coefficients only grow, so what I'm saying, the condition is met when we so expand this into some new Dirichlet series and turn this into a power series of q. Just put bn q to the n. Then this meets the condition. This actually, the denominators at 2 grow only logarithmically in n, and so there's grow polynomially in n, so they're sub-exponential, and so this is convergent also on the twoadic disk of radius 1. So these integrality properties are automatic in this setting. And now observe as an immediate corollary of this that already, for example, this conjecture of Hasse from the 1930s implies, well, this was proved, this was finally proved by the modularity theorem by Wiles et al. And we just said that the L function And of course, the Hasse VLL function of the elliptic curve will be just this, essentially, this L function that I had written all along. Okay, so this L is entire holomorphic with the right functional equation. Then since the integrality property is automatic, and then it implies, so you take n to be the conductor of the elliptic curve from the conjecture, and it implies full modularity. So as soon as you have this, no need to consider any twists, just this one L function, and of course the main problem is to somehow prove that it does have this analytic continuation with the nice properties. And I think I wanted to say a second example, and then conclude with the, and I just need to wrap up the idea of the proof. Okay, so this immediately contains theorems A and B up to arranging. So I'll just say it actually gives Euler products are not used, and it gives that if you have more generally elliptic, so this is a corollary, sorry. Elliptic modular forms have some weight and level, and then the product of their L functions has a holomorphic branch, holomorphic square root if and only if essentially the modular these forms are equal up to this kind of scaling one argument by a rational number and multiplying by a scalar. Only in the obvious case. And I'm saying that by this kind of trick with old form, scaling one of the arguments by some suitable integer, we can arrange that this thing does indeed, in the functional equation that it inherits from f and g, does have a integer conductor n, and so rather than the square root of an integer, and so it does fit into this setting of this integral converse theorem. So, okay, for 2 minutes, I want to say some the highlight of the proof. Yes, this does contain the unbounded denominators conjecture in the case of arbitrary finite index subgroups of SO2Z, just because if you have one modular form for this group gamma, then its Milan transform does have the analyticity properties, does have the functional equation, and so we are saying that it cannot have the arithmeticity properties. So we're saying that it must have some positive, must have some denominators. So does not have tau equals 0 expansion for, let's say, integer Dirichlet series. And the whole point in this is the realization that the proof, the way we go about this result, didn't have to be about the finite index subgroups, but it's about, by Hecke's lemma, this functional equation is really equivalent to modularity under a thin group, which is generated by just the two unipotents. That gives just the Fourier expansion, and the functional equation comes from, so it's 1, 0, and 1, which is of course contained in the Hecke congruence group and is dense for the congruence topology. So it's congruence closure gamma 0 n, and the functional equation with holomorphy, very importantly, rather than homomorphy, is equivalent to just modularity for this group, and so we can fit this into trying to prove if f of q is a classical modular form, and that lends well to arithmetic algebraization methods in the style of Yunqing's talk. Thank you very much for your attention. I will end here.
So are there any questions for the speaker?
Why did you say that your bound was optimal and the theorem?
On that board? Can you repeat it again? I apologize.
Why do you say that your bound is optimal?
Okay, it was not clear to me for some. It's not completely. It's not really obvious. It was explained to me by Alex Smith, but it's some explicit construction using the Chebyshev polynomials of this compact minus 2 root q that I'd be happy to discuss in person. It's not. Yeah, it's by an explicit construction.
It is optimal in the sense that there is an abelian variety for which this it's close to the optimal bound.
Yes, it's optimal in this aspect. Maybe ignore this coefficient, but this is the correct exponent of q in the asymptotic that, let's say, q goes to infinity first, and then n goes to infinity. Sorry, I want to think q is fixed and q is large, but n goes to infinity first. In that asymptotic, it is optimal. One thing I don't know is for Jacobians, actually, is this delta bounded away from 0 for a fixed q or not? But abelian varieties are just given by their aptoisogeny, or the Veil numbers. They're just questions about polynomials. And then we can give an explicit construction to show it's optimal.
When is delta 0?
Exactly when A is isogenous to the square of an abelian variety. So it's 0 if the Frobenius roots are exactly doubled up with even multiplicities. So I think of delta being very small as some quantitative version of almost doubled zeros. Yes, and so there is a quantity. Okay, it's one line to for the L functions case. The delta that I would define would be there's a similarly canonical pairing that, interlacing that you go in this sense, and then I take the sum of the segments and then multiply it by an exponentially decaying factor that comes from the decay of the gamma function. And then my question is, I guess I put this: can this ever be little of 1 for some family, for some L functions, let's say of GO2 type of elliptic modular forms, as a conductor for a fixed weight k, and the conductor going to infinity? The point is that these qualitative theorems have proofs by Diophantine methods, which in principle, in the end of the day, should lead to quantitative results. And this is the type of quantity that would be involved in these results, but it is work in progress.
So how different are the ingredients to the proof of this theorem to your original proof of the Amala denominator?
The bulk of the proof is the same, but the different part is that it only. So let's say it comes in two steps. That first, as soon as I show, so I'm trying to prove that this big F is some classical modular form. If I divide by some form of the same weight, like the kth power of the theta function, then I'm trying to prove, first of all, that F is an algebraic function of lambda that gives some contact with arithmetic algebraistic criteria. And as soon as I do that, so as soon as this is proved algebraic, which is by exactly the method of our paper, then all of a sudden we have gamma, some finite index subgroup of SO2Z, under which the F is modular. And at this point, we're just reduced to our paper. As soon as we have this gamma. So this is a little extra argument to arrange this, and that's the same method. in one word, the point is that Andre's algebraicity criterion can recognize the algebraicity for even for if we have modular form under the thin group. In this sense, with functional equation translates to modularity under the thin group. So one modular symmetry already gives the extra overconvergence for applying Andre's algebraicity criterion.
So if I could just summarize, in this integral converse theorem, you've removed this twist, initial this vague converse theorem condition on existing functional equations with a twist, but you've replaced it with this
integrality. Okay. Exactly. And Bucher's version was something different, but so he didn't consider integral coefficient at all. He allows meromorphism of twists. I don't know if the methods can speak to each other in some sense, but we do a different thing.
Okay, so if there are no other questions, then thank the speaker again.